Okay, so we are going to start this technical seminar is due to that the service has got recently a new equipment. So the idea is to present the new equipment and how it works and all the other details. So for the reason, Marco is going to present it.
Okay, so this is the outline of the talk. We are going to introduce the technique, the equipment that we have acquired, the access mode of to the equipment within the ICMAB. And I will mainly focus on the examples of the samples that we have measured of the institute in order to see which is the application that we could have. So optical profilometry is a non-contact surface technique that uses a interaction, or you shine the surface with the light and you collect the reflection of this light, and by different techniques that could be interferometry, confocal, or focus variation, you measure the surface topography. And you can construct a 3D map, let's say, of the surface. The advantages is that it's non-destructive, easy to use, and very fast compared to AFM, for instance. Vertical resolution is very, very high, sub-nanometer, and is also very suitable for large heights and large areas. On the disadvantages, not all the surfaces are, you can't measure all the surfaces, have to reflect the light, or, I mean, if it is transparent, for instance, you can't measure it. The lateral resolution is also limited by the diffraction limit of light. And when we are facing situations like vertical walls or deep trenches and so on, it can have difficulties. And especially for dissimilar material, that is a term that in this technique community is widely used. When you are having two different surfaces that optically are different, you have to be very, very careful when to quantify the difference on height. Okay, I will show many examples on that. Our approach has been mainly experimental. So we have been comparing data of AFM and optical perfilometry, rather than theoretical. But I will explain very briefly how do you measure or how do you scan the surface. Okay, so you have your equipment, you have your surface, you shine your surface with a certain light, and there are different techniques that you can use to study this interaction or this light that you are collecting. And the different companies are offering different techniques, and all of them, they claim that theirs is the best. But the interferometry is widely used. Okay, then the theta dot is of one company, confocal is of different companies, and so on. But all the equipment that I have tested, they are doing the same. You are scanning the set with the head, with a motor or with a piezoelectric, and let's say you set a minimum height, a maximum height, so you define a certain theta range. Then you launch the measurement, and the scanner scans in this theta and looks for the points that, let's say, they have a positive interferometry or confocal or whatever, different, the points on the surface that are giving a positive answer. So with all this collection of data, the software is doing a profile, and if you collect many profiles in 2D, you collect a 3D image, and the software reconstructs this surface. So this is the operational mode for most of the of the equipment. So our approach, I've said that it has been mainly experimental and is quite limited, okay? I have devoted like 5 days in total, a demo in ICMAB, a short stay in the Institute of Material Science of Madrid and the Polymer Institute in Madrid, and 2 days in the Sensofar company that is located in Tarrasa. And those are the equipment that I have tested. I am not going to enter into detail. And the number of samples that we have been measuring are quite large. And I think that they represent a wide range of systems of the Institute. In parallel, I want to acknowledge all the people that has been giving me feedback of the technique and also giving me training, especially Paco from Scientech, Joan from ICFO, and Juan Carlos from the Material Science Institute of Sevilla, that they were very friendly, and I have discussed with them the technique. So the profilometer that we finally chose is this Profil 3D that is based in light interferometry. And we got it and was financed by the FAS, plus ICMAB budget and also budget from the service. What we got for is we have light interferometry by white light, green light, this phase shift interferometry that is very interesting for very thin or small height measurements below 300 nanometers, I think. And we have 2 objectives. The software capability of stitching that I will show a few examples, a PSI calibration grid that we didn't know, but we got it in the last moment, and I think is really necessary. And we also got an extra license for analysis. About possible upgrades for the future, those are a list of what I mean that can be upgraded. From my point of view, an active vibration isolation table would be the first option for me, and it's gonna improve a lot the performance of the equipment. And also a 20 per objective would be also helpful. The 100 also, but it's very, very expensive. Then there are these software possibilities that I would suggest to test them with the company and to see if they are, I mean, interesting. I don't see them like a priority now. About the software, the acquisition software is this Profil from Filmetrics. It's not a user-friendly software for me for 2025, but it offers options for measuring that other companies they don't offer. Okay, this is an example of how do you have to access to different locations to, for instance, get to the grid mode or change this parameter in the fitting of the interferometry. That is really important. This valid, so you have to enter here, then go here. For setting different setup of materials, you have to go there. I mean, it's not user-friendly, but it's really, I think it's helping a lot to have these options, okay? About the software for the analysis, I already we have this Filmetrics software, and the data is also exportable to SURF format and also TXT. The SURF can be opened with Gideon and also MountainSmap. And the TXT I have tested that WSXM is open, Python of course, Origin also. I don't recommend it, but it's an option. From my point of view, for particular analysis, the stitching for me, it's recommendable to do it with Filmetrics, okay? And it's doing it, I think, very well. The mountains is also working nicely, but since it is the same software, it's doing it directly and better. Particular treatment for optical profilometry that I wasn't familiar with, the removal of outlines or fill invalid pixels. These three software are doing it, but I would recommend to use the Filmetrics, then digital, and Gideon also, but it's not that direct to do it. And for the height of dissimilar materials, Filmetrics already has an option on that. And we have contacted the Digital Surf to implement something related to that on the mountains. About the location, so most of you already know, but we are in MatGas in the 104 lab. This is the sketch of the lab with the two AFMs in here, the desktops, let's say. And this location in here is going to be devoted to this equipment, to the Profilometry 3D. And we are going to have, for the moment, a measuring PC. And in future, we will have an analysis PC that it will be available not only for analyzing data of the Profilometry 3D, but also AFM or whatever you need. So we decided that it's going to be a self-use mode for this equipment, for both for the equipment and also the analysis. The fees are still not defined, so we are working on that. But what we will, or what we want to do now in the 2025 is to train the people that is going to be using it. So we already informed the PIs a few days ago. And if you are interested in getting trained to the equipment, write me before next Monday 12th, and I will write you. And since we are going to have limited time before the end of the year, we will prioritize to train at least one person of the group that is interested on getting the training. So, as I said, our approach has been more experimental than theoretical, and we have been verifying the validity of the technique for different samples of ICMAB. When possible, we have been combining both AFM and optical profilometry. So I will start showing some examples, and I will start showing examples of homogeneous samples, homogeneous optically speaking, okay, that you are having, let's say, the same kind of material all over the sample. And then I will pass to samples that are containing or coexisting dissimilar materials, okay? So this is an example of Alexander and Fatemet. It's a copper foil that they use for the reactions or the batteries and so on. So what I did here is to stitch 64 AFM images with a certain pixel size to get more or less the same lateral resolution by AFM than what I was expecting for the interferometry, okay? And the topographies that we are getting are quite similar. It's not the same location, okay? And the roughness that we are getting is, it agrees, okay, with the two techniques. Another example, the same approach, stitching 25 images and getting a lateral resolution of hundreds of nanometers for an oxide from the group of Teresa. And we are also getting the roughness. Both values are very similar, okay? This is an example of another metal, stainless steel, from Albert and Laura, where they mechanized this stainless steel, and we are getting also not that in agreement, but it's in the range, okay? And it's really dependent on the location. you can see that the lateral resolution in AFM is much better in this case, as expected. Another example, in this case, we are passing to a ceramic from the group of Martí and a much rounder surface. We are having a roundness of 2 microns and nearly reaching the 10 microns height. Okay, this is in the limit of the scanner that we are having in the AFM, and in fact, in this location is the scanner is saturated. Okay, but the roundnesses that we are getting for the two techniques are comparable. And here, what I am marking for these examples and others in the future is the size of the image of the AFM is not the same location, okay? But this is the size. You can compare the features and see that the interferometry is working nicely for this surface. This is an example of 3 different samples from Angel that he's doing different laser treatments to these Papix graphite layers. And we saw how the roundness of the surface is increasing a lot. And this measurement, I mean, these 2 samples would be possible to measure by AFM, but this not with the scanner, that at least with a scanner that we have available in the lab. More examples, a thin film of LSMO, an oxide of 100 nanometer transferred to a PET polymeric substrate that forms the wrinkle formation that we have been studying by AFM. And if we measure them by interferometry, and in this case, we are stitching 4 different images of profilometry, we get same heights. Again, it's not the same location, okay? So don't look for, I mean, but the heights on the wrinkles are comparable. This is an example of the group of Agustin, where they are having pillars and holes on a silicon matrix. To measure these samples by AFM is, I mean, we didn't reach the bottom because for these holes samples, they were expecting 5 microns, and we measured it, I think, very nicely. And to enter the tip of the AFM here, I mean, you are not gonna reach the bottom since you have the apex ratio of the tip. And an example of a measurement that was done in the demo of ICMAB that has been published recently by Anna, Martí, and co-workers is this BC fiber structure where we were able to measure the roundness on 2 different samples. And this is an example of measurements done in ICMAB without the active vibration isolated table. Okay, so I am very happy to see that data from the lab could be already published. And now we are entering a bit in the border. Okay, here we have 2 samples from Godney and Shima. In here, they have a perovskite on silicon, but a full layer, okay? And we can measure the roundness, and I trust quite a lot this measurement. But when they are having not full covered surface, we are getting heights of hundreds of nanometers with the silicon. I don't have the AFM of this sample, but I don't completely trust this height, also relying on the experience that I have with other samples on silicon. Okay. Another example that is a bit in the border is those organic materials from Alexandra and Marta. They have here the gold electrodes and here the organic material. those are the measurements by optical profilometry. And we see that the gold electrodes, they look lower. And I am not sure if we are measuring this difference on height properly, okay? I doubt it. If we compare the roughnesses that we measure by AFM in 20 micron square, we are in the range, but of course the lateral resolution that we are having with the optical profilometer is not reaching the AFM, okay, for this data. And now we pass to measure heights of two different materials, let's say. For in this case, we are having an organic layer, and Julia et al. They have performed here a scratch to have the bare glass that I think is covered with a metal, and we can measure by AFM the difference on height that is like 160, 170 nanometers, and depending how do we measure the same scratch with optical profilometry with two different fitting modes, the centroid of the envelope peak, we get a very nice, I mean, the same result, 170, but with the envelope peak at the same very location, we get 440 nanometers, okay? So this is an example of how careful do we have to be when measuring step heights of two different materials, and also about the conditions and the method that we are using for the profilometry, okay? So this centroid for this case was working nicely, this envelope peak wasn't. So for the examples that I am gonna show in now, what I have been doing is, if I am having the AFM, try to get the best conditions for fitting the results, let's say, and getting this condition for each system. So for instance, this is an example from Arantxa, Nuria, and Rosella. They have these curcuminoid materials, these sheets here in silicon, and they have a metal here, I think it's called, but I'm not sure, and also covered by this organic compound. And by AFM, we can correlate the optical microscopy with AFM, measure the height, and so on. When we go to profilometry, very same location, we see that the contrast on the organic layer is inverted. So it looks lower than the silicon. But the difference on height between the electrode and the silicon, in this case, is okay. Okay. So this is an example that for measuring these organics, we have to be careful. And I changed the different conditions that I mentioned, and I didn't get to invert this contrast. Another example of an organic layer on silicon from Alba, Esther and Carmen. They are having this polystyrene on silicon, and they performed a scratch, so we measured it by AFM around 23 nanometers. And by playing with the dissimilar material option in the analysis process, I got to get the same result. That for me was quite surprising. Okay, but it fitted like perfectly in this case. Another example of success is these electrodes from Jan and Sylvia. They are having an oxide here, and here an electrode of nitride and platinum. And for this particular thickness, we got good results, also working with this dissimilar material option on the software in the post-treatment, okay? So we could, let's say, for a set of different samples of different thicknesses of this kind, we could set like a recipe for analyzing this data. So in this case, this is an example of a step on a YBCO versus copper from the group of Teresa. This is the AFM, and this is around 500, 600 nanometers. And you can see that by profilometry, we get 3 times more the height that we are getting by AFM, okay? So not only for organic, for inorganic also, we are getting wrong results many times. Another example of a device from Yanendra and Yerbasi. This is the image of profilometry, and the image looks great, super nice, but you can notice that the contrast is inverted. This is higher, and here is lower, okay? This is an example of, for me, that you can get very nice images, but wrong height, and that you have to be careful. In fact, here you are having three different surfaces: a metal, an oxide or silicon, and the 2D material. Another example of this kind of device from Matteo and Jan, and we are facing the same situation, okay? You can see here, this is the very same also device, and you can see that here, the height contrast is also inverted, okay? What we are trying to do, or we have been talking to the people of Digital Surf for the software on mountains, and we are suggesting that they could maybe implement some combination of AFM or other mechanical technique to combine it with this kind of data to recalibrate the data of the profilometry. I think it could be very interesting because to get this image with spikes and problems and so on is at least 15-20 minutes. This image, you can get it in 2 minutes, okay? So if you get a recipe or after measuring one line of AFM, you can extract the height in this line, for instance, and recalibrate a nice image like this one or the one of Yanendra, would be very advantageous. And to finish, an example of large area stitching. I did it this week, overnight. It took like 378 images that were nearly 5 hours, but if you do the counts, it's less than a minute per image, okay? So this is showing you how fast the technique is when you have it, when you already have the conditions to do a measurement is very fast, okay? And so I finish with a summary. So I think that the technique is gonna be, or is interesting to apply it in different systems of the institute, and that can be that is applicable from thin films to very, very rough surfaces that we can't access to this kind of characterization by AFM, okay? The vertical resolution is very high, and it's a measurement that is fast, and you preserve the sample. And what already mentioned, that is fast, easy to use, but the challenge, the accurate height of quantification with the similar materials for me is very challenging. And all the discussion that I have had with ICFO, the Material Science Institute of Madrid, and the one of Sevilla, they are facing the same situation. So whenever you face a new system, you have to combine optical profilometry with some mechanical technique. Could be profilometry, mechanical, or AFM. And that's all. Thank you for your attention.